Hello everyone, today I'm going to introduce wind turbine power generation forecast. Wind power is becoming an increasingly important renewable energy source in our daily life. Not only does wind power help alleviate the energy crisis, but it also responds positively to increased environmental awareness and concern about dependence on traditional fossil fuels. According to the latest statistics, wind power is growing at an alarming rate, especially in China, with an annual growth rate of 178.6 TWh, which is a sign that wind will become the dominant energy source in the future. Nowadays, problems with energy supply and use are related not only to global warming, but also to such environmental concerns. In contrast, wind turbines are a significant help to the environment. The dataset we have collected is from cargo and it contains a lot of attributes, which is time, power generated, and some weather data like wind speed and wind direction. It records every 10 minutes from January 2018 till March 2020. The aim of this project is to predict the power generations. So the regression model and the time series prediction model is our best choice. The time series prediction model is to solve the time series problem. The four model we are using in this project is linear regression, random forest, ARIMA model, and ARIMAX model. Linear regression provides us with a basic forecasting model. It assumes a linear relationship between the wind speed and wind power generation. This model is easier to understand and implement, but may not be accurate enough in the face of outlier and non-linear relationship. Further, we're using a random forest model. This model is based on the multiple decision trees, and it is able to handle complex non-linear problems that cannot be solved by linear regression. It is very resistant to outliers and provides higher prediction accuracy. To solve the time series problems, we need to use a remote model, which is a combination of autoregressive and moving average method. It is able to handle trend and seasonality in data, but may require preprocessing for some non-stationary series. Last, about the SARIMAX model, which adds seasonal consideration to ARIMA that can capture and predict the seasonal change in wind power generation. Before we get into the model, we have to deal with our data. So we have to deal with the missing data. We have to replace those missing data to value 0, and we're gonna change our index to the data type to make it usable. To build a linear regression, we need to select X and Y features. A Y feature is our power generate column, and the X feature should be the other column without the power generate. So when we select that, we need to process our X using standard Scala and the PAC. Then we can separate the trains and test it to train the data, and then to train the model, and then we using model to predict the power generation. As you can see, the result is here, and it is predict the data, and the mean square error is quite a lot, and the fitness score is kind of low, which is 0.64, and you can see it somehow it reached to the -1, which is bad performance as a linear regression. So linear regression is not fit with this dataset. A random forest model is the same step with linear regression, but the result is look much better, which has a really low mean square error, and fitness score is almost reached to 1, which has really perfect performance for prediction of wind turbine power generation. Then time series is different. The feature we're using in here is using time as our features, and we need to get three parameters by using ACF power graph and PACF, and using ADF method to check if the data is stable. Once we get these three parameters, and we can use our ARIMA model to predict our power generation, but the result looks not really good. As a fitness score, it reached to a negative value, and mean square error is really high, so it's a really bad performance in this model. The last one is Sarimax model, and it is based on ARIMA, and the only parameter is required and needed is the seasonal circle, and we input 12 as our seasonal circle value. From this value, from this model, you can see it's much better, and the mean square error is the lowest one, but the fitness score is not that good. But even though the fitness score is not that high, but the mean square error is the lowest one, which means it has a perfect prediction of the wind turbine. So each model has its strengths and limitation. Linear regression is easy to understand but may not be flexible enough. Random forest model take a lot of time to train and in the decision trees, and difficult to achieving incremental learning. For the time series model, can observe anything other than time series. In this data-driven era, we have ability to use historical data to predict and shape the future. For wind power, this means we can manage energy resources more efficiently, better plan maintenance cycle, and automatically achieve more sustainable energy production. Whilst each model has its strengths and limitations, by using them in combination, we are able to predict the future of wind power with unprecedented accuracy and insight. Rather than trying to control the wind, we are learning how to follow its direction and harness its power more intelligently.